Welcome to section number 4, where we are going to be talking about fluid level surveys or fluid level shots. And this is exciting. So the first 3 sections of this course have pretty much been introductory, just to make sure everybody's on the same level. I gave you an introduction to fluid level shots in the last section, but now we're going to start getting down into the weeds and getting into our diagnostic tools in the next 5 sections. And we're going to start off with the fluid level gun, which lets us look down the annulus. And you might be feeling like this little dino pup with his fluid gun right here and not feel too confident exactly in how a fluid level shot works or how to interpret it. But by the end of this section, you should be pretty good at interpreting fluid level shots, and I would say pretty expert on it, especially relative to most. And then by the end of the second fluid level shot section, you will be a master at it, I promise. So what are we going to talk about in this section? Here is the overview. So first off, we're going to talk about fluid level shot theory. So we're going to look at the fluid level gun and how generating that pressure pulse and shooting it down the annulus and getting the reflections back, how do we interpret that? And in order to interpret it, we have to understand the polarity and amplitude of kicks. So this is an acoustic trace. This is the recording that comes from a fluid level shot. And this is a recording from the microphone right here. Here is the shot. And you can see we have various different kicks down here. A down kick, up kick. We have a lot of up kicks right here for these perforations. And then here is the fluid level. So what's important is the fact that there is a polarity to the kicks, down kicks and up kicks, indicating different things, but also the amplitude of the kick. How much does it deviate away from this zero baseline right here? So basically the height of the kick indicates how much energy is reflected. So we're going to look at that and look at lots of examples. So we have plenty of examples to look at to kind of ground your knowledge in interpreting the acoustic trace. And then we're going to talk about casing pressure buildup test, which is used to approximate how much gas is flowing up the annulus. This is something you do after the fluid level shot, and it's very important in calculating approximately how much gas-free liquid is down there above the pump. So we'll look at examples of that. And then we're going to go into a big section here on calculating the acoustic velocity. So just because you can see a fluid level kick does not mean you know the depth of that fluid level unless you know how fast the pressure wave is traveling down the annulus. And there are 3 different methods for calculating the acoustic velocity: the collar count, the downhole marker method, which is what I used right here. I told the software that I know that that kick is the tubing anchor and I know the depth, and it can then use that to calculate the velocity at which that pressure wave is moving down the annulus. So, and then we have another method, the specific gravity, or really we can just kind of approximate it from the specific gravity, or maybe just copy over an acoustic velocity from an offset well. So we'll look at how to apply those. And then after that, at the end of this section, we're going to look at other considerations. So what we're going to be focused on is really trying to have a good acoustic trace that we can interpret, like this one right here. It's quite clear, but sometimes you have more difficult wells to see down. So we're going to look at background noise. Background noise can be created by gas bubbling up through liquid, so it can be coming from downhole. It can also be coming from something at surface, like the pumping unit running or potentially a chemical pump. So we'll look at examples of that and how to minimize background noise. We'll talk about shot size. What is the appropriate shot to take? How much should we pressure up the volume chamber right here? And then we're going to really just focus on getting good clarity of shots, okay, with respect to several different topics. So that'll finish out the end of this section. And then the second fluid level shot section, I believe that is section 7, we're going to look at troubleshooting in more complicated repeats. Okay, so if you have acoustic traces that are more difficult to interpret, we're going to look at some of those examples. We will also look at some of those examples in this section, but we're going to look at a little bit more detail there, especially the mathematics as to how you calculate what is a repeat off of what. We're also going to look at different types of filters. So we have filters for the acoustic trace right here. We also have filters for our tubing collars. We'll talk about implosion shots with the 1500 PSI gun. That's where you shoot the pressure from the well into the gun. And we'll talk about producing bottom hole pressure, static bottom hole pressure, how to calculate those, and then tie those into the inflow performance relationship, which is a way to predict the maximum production you can get from a well. So this is what we're going to talk about here in this section. It's going to be all of these topics. This is going to be the second fluid level shot section. And just a friendly reminder that this work is copyright protected, and I would appreciate that you do not copy, share, or reproduce this work in any way. Please support my work. Thank you. So let's watch this video. This is an oldie but a goodie from Echometer here, and it shows you the principles of how a fluid level shot works in this old animation.
Before we get started, let's talk about how the process of taking a fluid level measurement works. First, the gas gun volume chamber is charged with compressed gas to a pressure greater than the casing pressure. The TWM software opens the solenoid gas valve,
That's the shot.
releasing the pressure charge from the volume chamber of the gas gun into the well bore. The acoustic pulse generated by the release of pressure travels down the casing, reflecting off of tubing collars and other changes in cross-sectional area. The depth from the gun to an anomaly in the casing annulus is directly proportional to the round-trip travel time for the acoustic pulse to travel from the gun down the casing gas to the anomaly and reflect back to the microphone in the gun. Finally, the remaining energy from the acoustic pulse is reflected back toward the microphone. These reflected pulses travel up the casing and are detected by the microphone in the gas gun. An accurate strain gauge pressure transducer measures the casing pressure buildup for several minutes after the liquid level measurement.
So that's basically it right there. You take a shot, it goes downhole, reflections come back to a microphone that are picked up, plotted on that acoustic trace, and then there is a casing pressure transducer, which on the old wired equipment, that's what we're looking at right here, it was kind of sticking outside. In the wireless equipment, it's internal, but it's just basically reading what the casing pressure is and turning that into something digital that's imported into the computer. So there's a lot going on this slide, but this is a new slide I just added, and I want to illustrate a point here. So when we take a shot, okay, we are creating a compressive wave that is traveling down the well. So you typically will pressure up your volume chamber here with CO2 or nitrogen. But when you take that shot, it's not like, let's say that this is nitrogen that you're shooting into the well. It's not like that nitrogen molecule is actually flying all the way down to the fluid level and then reflecting and coming back. What you're doing is you're creating a compressive wave in the gas medium that is then traveling downhole. And to illustrate this, let's look at a compressive wave in this slinky right here. So as I start this video, notice there's a compressive wave and you can see that the windings on that slinky are getting closer together. Okay, there were two compressive waves that just went from left to right. But notice the compressive wave transmitted through the medium, which is a slinky here, but the actual windings of the slinky are not actually moving themselves. They kind of get closer together, but they return to their original position. Obviously, it's tethered right here with this wire. So when we take a shot, we're just creating a compressive wave like this that is transmitting down through the gas medium. And that compressive wave is basically just a localized area of higher density. Okay, so this is, when we take a shot, this is what's happening. These green dots represent the compressive wave. It's going down and it's reflecting back off, and then it's coming up to surface. And then of course we have a microphone right here in the bottom of the gun. And all of the reflections coming back to surface are hitting that microphone, and they're being plotted down here in the acoustic trace. And this is nothing more than an amplitude of the sound waves that are being picked up. So we generate the shot, the boom. Okay, and that goes down, and any change in cross-sectional area will send a reflection back, and that is being recorded right here in the acoustic trace. And you can see we have various different types of kicks. Okay, there's a different polarity to them, down kick, up kick, but this is the recording from the microphone. So just keep in mind, it is a compressive wave. The gas molecules are actually not traveling, flying all the way down and reflecting back. So if we look at the acoustic trace, it has two different x-axes. So here on the y-axis, this is the amplitude of the sound wave that's returning back and vibrating the diaphragm here on the microphone. So this is the amplitude. And here on the upper x-axis, this is time. This is called the round trip travel time. We'll look at that here in a second. But this is when the shot occurred. And this just shows up when the pressure wave returns after reflecting off different things downhole. So this is time in seconds. And down here is the calculated depth. Okay, very important to understand and distinguish between these two, and we'll look at that here a little bit later on. But let's kind of zoom back out, okay? Taking a fluid level shot to determine the depth of the fluid level. This is known as acoustic echo ranging, okay? Because we're determining how far something is, ranging the distance of it by using an echo, getting a reflection off of it, okay? And this is quite similar to where, let's just say that if you were a Swiss goat herder, okay, and you're on the Swiss Alps, and you're doing a little yodelay, 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 hoo. If you do that and you direct your voice, let's say over to a specific mountain, and you had specific timing of when you made a sound and waited for that reflection to come back, you could actually calculate approximately the distance to that mountain over there. because there is a certain time of transmission as to how fast, when you make sound waves, when you start yodeling, that is going to travel all the way over, reflect back, and then come back to you. And based on the acoustic velocity in the atmosphere, in these cold mountains right here, you can calculate the distance to the top of that mountain. Okay, bats also use this principle of echo ranging, and it's called echolocation. So bats have poor eyesight. They're flying around in the dark, and the way that they find their food, or probably avoid trees as they're flying at night, is they send out these little echoes that reflect off things, and it comes back, and they're able to interpret their surroundings. Okay, so working on the same principle. Sonar also works on the same principle. So sonar stands for sound navigation and ranging. So you can use sonar to determine how far off the seabed is so that you don't ground the ship. You're going to send some sort of pulse down to reflect off the seabed, come back to a receiver, and you can calculate the distance to the seabed. Of course, the wave that you're generating is going to travel much faster in liquid than it does in air. It's about 5 times faster. You can also use sonar to determine if there's any submarines or any enemies out there floating around in the water, if you were to transmit that signal somewhere radially around the ship right there. And here's another example of using echoes. Now, this is really just a guy that's kind of playing around here with himself. He's playing with his echo. So he's playing his saxophone into this pipeline, which is about to be lowered down into this trench right here. And apparently the end of that pipeline is capped off because an echo is coming back. You know what, guys? It's section 4. We gotta let our hair down. We gotta dance a little bit. We're about to be learning. Feel the funk. A little too much, right? Okay, anyways, this is the same principle that we're using for a fluid level shot, okay? Quite straightforward. So have you ever thought about why Echometer picked the name Echometer? Think about it. Echometer. Distance using echoes. That's exactly right. So this is the 1500 PSI wireless fluid level gun from Echometer. If you have a different type of fluid level gun, it's okay. You probably have the exact same principles going on. This is the most common type of Echometer fluid level gun out there. This is the only one that I own. I have 3 of these. Okay, they have some higher pressure ones, which I do not own. I'll show you that in an upcoming slide. But let me show you the basic components of this fluid level gun. So first off, we have the volume chamber with a pressure gauge right here. This is what we are going to pressure up. Okay, this is going to be at a higher pressure than the casing to generate the shot. Then we have the microphone right down here in the bottom where you screw it on to the wellhead. And then we have 2 different things going on in here. We have the solenoid valve. This is the fast-acting valve that releases the pressure pulse into the well. And then we also have a pressure transducer, which is just recording the casing pressure. And there's a few other things. It's got some buttons here. It's got an internal battery. This is the bleed-off valve right here. So once you close off the casing, you can bleed off the pressure, that sort of thing. But those are the most important components when it comes to this gun. Now let me show you the internals of actually how a fluid level shot works. Let's watch this.
The dart valve releases gas from behind a 1/2-inch movable piston that allows gas from the gas gun volume chamber to flow into the well.
Boom, that is the shot. Okay, now you probably didn't pick up all of that. Let me show you what's happening. So this is the volume chamber right here. We have 2 moving items in this gun. Okay, we have the gas valve, which you can see right here, and then we have the dart valve, which is right here. So when you tell the software, shoot, okay, take the shot, what happens is it opens this dart valve, and some gas is going to come out of this little weep hole. Okay, if you've ever taken a shot close to the dirt, sometimes you might notice that it kicks up some of the dust on the ground, and you're like, whoa, where did that come from? Well, some of the gas initially shoots out the side of the gun, and that creates a lower pressure right here, and this causes the gas valve to then slide up. And once it slides up, all of the pressure in the pressure chamber can then cycle around it, because this gas valve is creating the pressure seal right here. Okay, and so if you look at this image, this is kind of a different illustration. It shows this really long neck. This is the O-ring right here. That is that O-ring. It does not have as long of a neck right there. Okay, but this is the primary O-ring that is holding the pressure in the volume chamber. So if your fluid level gun is leaking pressure out the bottom where the threads are, that would indicate that you have a bad O-ring right here. And if you have gas that's leaking out the little weep hole on the side of the gun, that would indicate that your dart valve is not sealing, and you would need to do maintenance on that. But let's go ahead and watch that again. Remember, this opens, it drops the pressure here, which causes the gas valve to move up, and once it does, the pressure can equalize around from the volume chamber. So gas goes out, it moves up, boom. This is how you discharge the shot into the well. So most of the maintenance that you will have on this fluid level gun is going to be this O-ring primarily right here. This is what seals. This is a wiping O-ring. It's not holding the pressure seal. It's just to try and wipe it and keep it clean so you don't get as much dirt right here on this particular valve. So here's some really crappy wells. Let me put it this way. So I was contracted, this is a while back, I was contracted to take a lot of fluid level shots. These were called H15 tests in Texas, which means that these are inactive wells. And the regulatory body wants to verify the fluid level in these inactive wells is not above the drinkable water zone. Because if there's a casing leak, they don't want you to contaminate the fresh water zone. Anyways, I was doing a lot of these shots, and a lot of the wells look like this, or even this. This is a well right here. There is no casing head. I've never seen anything like this in my life. And so I'm using this map, finding these wells, okay, very difficult, but they don't even have anything for me to screw onto, and it's just an open top piece of casing. And so anyways, I found this tubing wiping rubber that my fluid level gun is sitting on. This is something used on a pulling unit to wipe the outside of the tubing to make it clean. And I found this on one of the locations, and I started sitting my gun on top of it and taking fluid level shots, and it actually worked. It helped to kind of centralize the focus of the energy back enough to the microphone to detect where the fluid level was. And I made a little video of this one right here. So this one's down on the ground, but you're going to see the shot. So fire in the hole. Shot. Watch for the reflection. There's the reflection. You see that puff coming back of that dust? So the shot, you could see the air come out, and then it went down, reflected off the top of the fluid level. We could see it come back. That is a fluid level shot. So here are the steps for a fluid level shot. Okay, first thing is you're going to pressure up the gun. You want a delta P, or pressure differential, of 300 psi plus. Okay, it depends on the well and what you want to do. It's not uncommon for me to have a pressure differential of 1,000, okay, depending on how deep the fluid level is and how hard it is to see. But we're going to pressure up the gun. We want to make sure we got more pressure than what is on the well. Then you're going to connect it to the casing right here. You can see it's screwed on. If you have a slipstream, you're going to want to shut that off. So a slipstream, if you have continuous chemical, if you had a chemical tank with a chemical pump that was injecting chemical here into the casing, it's quite common that you have a slipstream, which is taking some of the produced fluids from the tubing, and it's tied right here to the casing to help carry that chemical downhole. Okay, so it's basically taking a little of the tubing fluid and circulating it back down. We're going to want to shut that off, though, for the shot, because that will create noise. Okay, so you will shut that off. Then you're going to open the casing to the gun. So at this point, we've got it all connected. Open the casing to the gun, but you want to do it slowly. You always want to open valve slowly. Sometimes you'll find surprisingly high pressure on the other side. I'll tell you a story about that in a little bit. But now we open it up. Okay, then we shut the casing valve to the flow line. So now we are connected here, and we're going to close this off. At this point, the annulus, or the casing, has been isolated. The gas that is flowing up that was going down the flow line can no longer do that. It's being trapped. And my gun is looking down the annulus. And so we're about to confine that pressure pulse to all going down hole and not going down the flow line. It's important to shut this off because that greatly reduces, if the well's making gas, that greatly reduces the background noise. So after you shut it off, you're going to observe the background noise. So this is a wireless gun right here. And so I've got my laptop hooked up with my wireless communicator for the Echometer system, and it's communicating with Bluetooth here, and I'm going to look at the background noise as to what's going on before I take the shot. Once I'm satisfied that it's low enough or I don't need to adjust anything, I'm going to go ahead and take the shot. Boom. So at that point, I release the pressure pulse, which is going to travel down hole. Okay, this is our acoustic pulse. It's going to come back to the microphone, and I'm going to have my acoustic trace, and I'm going to verify then that I have a good fluid level kick. Okay, it was a good test. And then also adjust my acoustic velocity method to calculate the distance to the fluid level. We'll talk about that, but make sure it is a good acoustic trace. If it's not, you're going to want to reshoot the well, maybe with a higher pressure. After taking the fluid level shot, you perform a casing pressure buildup test. So we're going to see how fast the casing pressure rises, and that's going to go into a correlation to approximate how much gas is coming up the annulus. So remember, the gas that's coming up, it's trapped now because this is closed off, and so we're going to see an increase in casing pressure if it is producing gas. In this particular case, it's increasing 1.15 psi per minute. After that, I'm going to open the valve to the flow line. Okay, so I'm done with the test. I end the recording. I'm going to open this back up to the flow line. If I had a slipstream I closed off, make sure you open that back up. And then we are going to remove the gun. So I'm going to close the casing valve and then bleed off the pressure. I'll close this off here, bleed off the pressure, make sure I don't breathe in the gas. You never know what's in there. And then we're done. We take it off and we can move on to the next well. Okay, so this whole process right here will take you probably about 3-4 minutes. It's very quick. It's unbelievably quick. Now, there's a couple important things to keep in mind. Okay, when you first connect the gun to the well, you want to make sure before you open up the well to the gun that you have a higher pressure here in the gun than is in the well. Because if you do not, the pressure is going to blow into the gun. Now, that's not a problem. The problem is that there can be solids right here in the valves that will blow into your gun. And this is going to create maintenance issues, especially with that gas valve that we saw that's sliding up and down. If you put a couple pieces of scale or solids or sand in there, it's going to lock up and you're going to cut up your O-rings. You're going to have to do more maintenance. So you always want to make sure that the gun is pressured up higher than the well. Another thing to keep in mind, in what some people forget when they're new at this, is don't forget to open the flow line up when you're done with a shot. This is pretty obvious, right? But you shut in the casing flow line. When you're done with the test and you take your gun off, do not forget to open that back up. And what I always do is I leave my crescent wrench right there. Okay, just to make sure that if I go to the next location and I don't have my crescent wrench, well, that's because I left it right here by the closed valve and I did not open this valve up. So even if it has a handle, like this one does right here, I'll still put my crescent so I don't forget. But it's not uncommon that people accidentally leave these closed, and if you do, they're going to build to a very high pressure, and somebody's going to get mad at you for doing that. So don't forget to open this back up when you're done with the test. So here is a fluid level shot being taken here in the software. So let me go ahead and play this video. So I start the recording here, and I'm currently recording the background noise. So the gun's hooked up, the flow line is closed, the casing valve to the flow line's closed. Here's the background noise. I just took the shot, and I've sped this video up just for time here, so it's going a little bit faster. But this is the acoustic trace. It's recording the sound waves coming back. We have a nice kick, and then we have a little down kick. Okay. So after I get it back, I'm going to adjust that liquid level marker for the fluid level. That is our fluid level. And then I'm going to tell the software that big up kick at the top, that is the top perforation. So I'm using the downhole marker method for calculating the acoustic velocity. And after that, I have the depth to my fluid level, which is 7807. And now I'm doing the casing pressure buildup test. And if you see down here, it's approximating 112 MCF per day. And that's it. So you finish the casing pressure buildup test, you'll hit the button, end pressure buildup, and then you're done. Okay, and then you can write your notes right here as to what the current runtime was, what's the information off the POC, any analysis you want, and basically you're finished. That is a fluid level shot. So fluid level shot safety, I expected you on this video. So if you recall, Deputy Dan is our safety coordinator here at Downhole Diagnostic, and he has a word of caution or safety for you. What's on your mind, Dan? Safety first. That's right. Good old safety man saying. So let's talk about a little bit of safety here when it comes to fluid level shots. Okay. The first thing that you want to really think about, well, there's a couple things, but this one is quite important, especially on high pressure wells. What is the pressure rating of the equipment? Okay. So if you look at this fluid level shot, this is a very unusual setup. Here's my gun. Okay. It's upside down, and this is a gas lift well, but it's an annular gas lift well, which means that they are injecting gas down the tubing. And if you're taking a fluid level shot on a gas lift well, you're going to be shooting down the side where the gas is injecting. Typically on a gas lift well, you're injecting down the annulus, producing up the tubing. This one is injecting down the tubing, producing up the annulus because it's a new well with a high production rate. So anyways, there was no easy way to connect to this particular well. Okay, so I did not have an easy access point, and so the easiest thing to do was to tie onto this needle valve right here. Okay, and so I had to use a bunch of swedges and fittings to connect up to the 2-inch for my fluid level gun. Okay, so but you want to be aware, what is the pressure rating of this equipment you're hooking up? Because this was a well that had about 1,000 psi on it, and you want to make sure that the rating of the fittings you're attaching to it can withstand that pressure. So if you look at the pressure rating of nipples and fittings out here, at least in my part of the world, there's something known as the working pressure and the burst pressure, and this is what it is for the standard stuff in the oil field. So we have standard, extra heavy, and extra, extra heavy. Okay, so a standard nipple is rated up to 1,000 pounds of working pressure, which means it can have up to 1,000 pounds on it regularly, and it should hold. It has no burst pressure rating, though, because they do not want you to ever go above 1,000 psi. Okay, keep that in mind. Now, an extra heavy, the working pressure, which is the pressure it can work under normally, is rated to 2,000, and it should pop. It should burst at about 5,000. Okay, and then extra, extra heavy is going to be significantly higher. So the heavier it is, that means the thicker the wall of the metal and the more pressure it can hold. Also, the heavier it is and the less easy it is to work with. But what I would probably recommend, unless you're working with some extremely high pressure stuff, I don't ever see anything like this, but I just use all extra heavy. Okay, just be cautious if you're using any of these standard nipples, because you might accidentally hook it up to a well and you're not expecting high pressure, and it has high pressure. So keep in mind, this is also the pressure rating for new equipment. So equipment degrades with respect to time. Let me tell you a story, though. So there was an ESP well that I was contracted to shoot. And I hooked my gun up, and I put like 800 PSI on it. And then I opened the casing valve to my gun, and it was hard to open. I eventually got it open, and I could just hear the pressure just really high. And I looked at the pressure gauge, and it just absolutely wrapped around my pressure gauge. And I said, oh my, I shut the valve and said, oh my gosh, what's going on? And then I found out it had 2,200 PSI on the casing. And it had 2,200 PSI on the casing because the casing valve was closed. Okay, now I had no expectation to find that high of a pressure on the casing, because typically on an ESP well, the casing valve should be open. And so I thought it was a mistake. Actually, it was intentional. Somebody had told this operator it was better to produce the well with the casing valve closed. I don't exactly know why, and I don't agree, and I told him that. But anyways, the point of the story is that sometimes you find high pressure even when it's not expected, even when it shouldn't be. I've found over 1,000 PSI many times on rod pumping wells because somebody accidentally left the casing valve closed and nobody noticed. So that's why you want a pressure rating higher than you think you're going to actually need, because you don't want it to blow up in your face. That's going to be a bad day. So some other things to keep in mind is that Echometer recommends that you make up the fluid level gun at least 4+ rounds. So you turn the fluid level gun around 4 times as you're screwing it together. I'm going to recommend the same. I can tell you a lot of times, depending on the threads on the casing, that doesn't happen. Okay, so anyways, try to make it up as much. Make sure it's a tight fit before you open it. And that ties into the next point here. Especially if you have bad threads on the casing that you're trying to screw into, open the valve slowly. Okay, if you're not exactly sure if it's going to hold pressure, especially if it's a high pressure well, open it slowly and kind of pressure test everything and make sure nothing explodes and you don't die. And after you don't die, then you can open the valve fully. But if something were to pop, it's going to be much better if your valve is just barely cracked open and you have a small release of gas coming out, as opposed to a valve that's fully open, shooting out 1,000 PSI full bore here, just wide open 2-inch. So open valve slowly. If you have a high pressure well that you're shooting down, I would recommend, especially if it's down here on the casing and you want to open it slowly, use a cheater pipe that gets you a little bit further away from the well, and also gives you more control due to that leverage on how much you're opening it, just to make sure once you open it, everything holds. And then, of course, also H2S gas. Be careful of that in the direction of the wind. It will kill you. So I forget exactly what it does, but it is extremely toxic in small percentages. So if you breathe it in, it basically, I think, inhibits the ability of your cells to uptake oxygen, something like that. It kind of just kills you internally. But be careful of that. You don't want to breathe this in. You don't want to breathe in natural gas in general, right? So I basically take the principle that I don't want to breathe any of this in. And so once you shut off the well and you're bleeding off the gas, go upwind, or at least take a deep breath and move around a little bit, get a little bit away from it, let it bleed down before you put your head back down to take your gun off. Let's look at the different fluid level guns from Echometer. So the first is the 1500 PSI gun. Okay, and remember we talked about Echometer in this course. They dominate the market though, so I don't want to feel like I'm just pushing their product, but they dominate the market. They have the best equipment, the best software, and I think they make up probably 80-90% of the market share here in the United States. So most people are using this. They don't pay me anything. I have no affiliation with them except that I love them. But here's the Echometer 1500 PSI gun right here, and it comes in a wired version, which is the older, and then the wireless came out in 2014. There are different software packages that come standard with these guns. Okay, this is the old software, TWM. This is the new software, TAM. I'll talk about that on the next slide. They also have higher pressure guns though, so it's designed, you're not supposed to go above 1500 PSI with this particular gun. Remember, I just told you a story where I pressure tested it accidentally to 2200 PSI, and from my understanding, okay, don't hold me to this. Don't go above 1500 PSI in this gun. But from my understanding, they pressure test these guns to 3000 PSI. Okay, so anyways, you're not supposed to go above 1500 PSI. I have done that several times before. If a well's 1800 PSI, I'm okay with it. Again, open the valves slowly, be careful. But if you have higher pressure wells, 2000, 3000, 4000, this gun is not going to work, and you're going to need one of the 5K guns, 5,000 PSI or 15,000 PSI guns, okay? And this is what they look like right here. So with the fluid level guns, you can do explosion or implosion shots. Explosion is where you have a higher pressure in the chamber and you shoot into the well. An implosion shot is where the casing or the well has higher pressure and you shoot energy into the gun, okay? So there's different ways of doing it. There is a special way that you can do an implosion shot with this type of fluid level gun. It's designed for explosion only, but there is a workaround method that I've done many times, and it's something there, it's a backup, okay, and it's actually really helpful to know how to do. I'll teach you that in the second fluid level shot section. Now for the 5K gun, this is designed for explosion or implosion. You can do both of them equally well. Here is the volume chamber. This is where you would connect to the well right here, and this is the valve that you're going to open. So instead of that little sliding gas valve we looked at, it has a manual valve that you are going to open with your hand. And so you can shoot energy from here to the well or back into your gun, no problem. And it doesn't matter which way you shoot, it's creating a pressure pulse that's traveling down the well. The 15K gun, which I've never even seen, I know some people have this gun right here. I've never even seen one of these personally in use or somebody that owns one. And so, but in particular parts of the world, if you have really high pressure gas, you might need this. This one is designed for implosion only. So if you have a well that's got 6,000 PSI on it, okay, you're not going to have a pressure cylinder that you could pressure up your gun even to even get above that. So you're going to have to shoot the energy of the well into your particular gun. So there's also the Echometer strip chart gun. Okay, this is the old gun right here, and you might have seen some people in the old timers know exactly what I'm talking about. But this type of gun right here, this is analog before it was tied into a computer. So you had this box and there's a paper printout that comes out of this. So instead of analyzing the acoustic trace on a computer through software, you have a physical printout right here. And after you get the printout, you're going to lay it down on a table and you get this so-called 11-point divider right here. So this is the 11-point divider, and you're going to try and find the tubing collars. Okay, so this is the old version. I'm going to show you a video of that. Actually, there's a video right here. Let's watch this. So I was doing training with a guy, and he had one of these, and I said, that's cool. Let me take a video. So he pressures the gun up. Okay, the gun's leaking, so he tries to seal it off with his thumb, which is fantastic. Okay, now he's going to start the strip chart. Okay, so it's starting the printout right here, and once it gets to a certain place, he's going to pull the trigger right there. That was the shot. And now it is recording with the microphone, same principles. Recording with the microphone. And here is the paper printout. So with this, you're going to identify tubing collars, and right there is the fluid level that we are looking at. So that is the strip chart gun, okay? And it works great, but there's a lot of disadvantages to it, including the fact you have all these pieces of paper. I know a guy that used to take a lot of fluid level shots with these a long time ago, and you'd open his truck and there were strips of paper everywhere. Like he'd open a door and paper just starts flying out everywhere. So the big disadvantage to this is that it's not digital. You have to do the calculations manually, right? And then you can't store all the records like you can. Like I've got on some wells, I've got 500 fluid level shots. I can go look at all of them just sitting in my office. With all those strips of paper, you're not going to save all those pieces of paper. It would be a disaster. So lots of disadvantages to this. I'll show you another video a little bit better of how it works on the next slide. So alternatives to Echometer. There is a company called Sage Technologies, which is in the United States, that still sells fluid level equipment, also dynamometer equipment. I would say they're just kind of a cheaper knockoff version of Echometer. So I have not actually personally used their equipment. I've seen it a little bit, and essentially it's going to be a little bit cheaper. One thing to keep in mind, I don't want to say anything about their product, but a lot of people just focus on the equipment. A fluid level gun's a fluid level gun. Well, a fluid level gun's important, but also it's the software you're interfacing with. How good is the software that you're using to analyze and troubleshoot the well? Keep that in mind. But you could look them up. Also, Ludert was a German company, is a German company that used to be in the fluid level dynamometer market in the United States. They are still in the German market. They were trying to get back into the United States, but based on what I can see, they haven't really made a push again. I was talking to them many years back. They were trying to get back in, but I think they kind of looked at the fact that Echometer's kind of got the market and pulled out. But there might be some other alternatives. I know there's a Russian company that has some fluid level type equipment. So other things you can look at besides Echometer. What is important when we take a shot, the energy of the shot, that compressive wave that we are generating and that's going downhole, it is going to be equal to the pressure differential times the volume, okay? So the volume of the shot, all right? So how much are we pressuring up the gun? How much of a higher pressure is it than the casing? And what is the volume that we are injecting? So if we look at the volume chamber size for these guns right here, this is 12 cubic inches for the standard 1,500 pound gun. Okay, for this one, it's 7 cubic inches, so it's a little bit smaller, and this is only 1 cubic inch. Okay, and so you can see as you get to higher pressure guns, there's a smaller volume chamber because they're assuming that you're working with higher pressure. If there's higher pressure in a particular well, it's easier to get the acoustic waves to transmit and to show back up to the microphone. So you don't need as big of a volume chamber. But for example, if you were going to take a fluid level shot with this gun and this gun on the same well, and you pressured up both the volume chambers to 500 psi and took a shot, this one's going to give you a better response because it's got a larger volume chamber. So for the same pressure differential, it's got a larger volume chamber. It's going to work better. You're going to see more clarity. And then here on the old strip chart gun, it's got 10 cubic inches, but just something to keep in mind. We'll talk a little more about that at the end of this section. So let's watch another video about the strip chart gun. And I think it's so important to understand this because the principles of what we're working with in the modern software, it all comes from this older technology right here. So it's kind of interesting to see how this works. So I was at a rod pumping symposium, and this is Gustavo at Echometer that's giving me a demonstration of the strip chart.
So that's a Model M. We have a demo well here. So we turn on the Model M, and we see some first check electronics, some battery levels and so. And then we're simulating a fluid level shot here. Now the software is listening to the well and taking a shot now, and that's a shot, and we see the colors, and this well is kind of deep, so the fluid level will be deep, over 5,000 feet deep, and that's a liquid level there, right there.
All right, and you've got 11-point divider you can use here?
Yes, we have an 11-point divider, and you should spread this paper all over your table, start counting colors here, all the way down to the liquid level. The liquid level is less than 9 seconds. It's actually at, let's see here real quick, the liquid level is at 8.7 seconds, and we can count the colors all the way down. Okay.
So an interesting device. Okay, if you look at this printout right here, it's got two different charts. It's got the upper one, this is for looking for tubing collars, and then it has a low pass filter line, and this is more for identifying the fluid level kick. You know, another downside to this is that you can't do any post-processing. You can't apply filters on it after you take the shot. You can't zoom in and out like we can do in our software. But it's important to understand the principles of this because when you were doing it manually, there were things that you were doing when you have that 11-point divider to count collars that you had to do to calculate the fluid level. Now the software basically does that for you, and most people don't even know what's going on. The software will automatically count the tubing colors. Most of the time it's right. Sometimes it's not right, and you should always verify that the software is correct. Otherwise, you can have wildly wrong calculated fluid level depths. So right here, this is the color analysis in the TAM software. Here's the acoustic trace. That's our fluid level. Here's our color line. The software says it can see colors to this point, and this yellow interval is highlighted, or I should say the colors in this interval are blown up down here. And this is our 11-point divider. Okay, you see we've got all these lines right here. And so we're supposed to be doing the same thing that you were doing mechanically with that metal device in the software. The software does it on its own, but you want to verify. So Echometer software, this is the old software right here. Some people, unfortunately, are still using this software. You need to upgrade. This software is just not fun to work with. I hate when I do training with people and they use this software. It's painful almost to go back into it. But this is called TWM. Okay, Total Well Management. And it's a great piece of software, you know, back for like the year 2000, 2005. It's just that things have advanced and this software has not. So this is the standard software with the wired equipment. It was created around 1997. It was last updated 2012, so we're looking at about 12 years ago. Here's what the display looks like, and you can do all sorts of things in this software. There's lots of features. It's just not user-friendly. So here's what a fluid level shot looks like, and I will show you some demonstrations in Section 9 when we talk about Echometer equipment and software. I will show you how to use this particular software. If you're interested, you can actually jump to Section 9 and come back here if you want to get a feel for the Echometer software, both the TWM and the new software, TAM, and I'll show you how to build a well file and how to use all the different features in both softwares. So this is the new software. This is what we're going to be looking at throughout this course. And TAM stands for Total Asset Management. I like to think it stands for Texas A&M University. Whoop, because that's where I went to school, but it's Total Asset Management, and this is the standard software for the wireless equipment. It came out in 2014, which just happens to be the year I started my company. So thankfully, I was one of the first people to come out and get the wireless equipment and wireless software when I started Downhole Diagnostic. This software, both softwares, are free to download. So you can download them, go to their website, you can find it. It comes with some example files for fluid level shots and dynamometer test and valve test. So you should play around with them, and really you should just play around with this one. Don't use this if you don't have to. What you should know though is if you are using this equipment, you can buy a license to use, essentially if you want to record on site, if you want to actually get data from a well, if you have wired equipment, you can pay for a license fee to use this software to actually record the data. If you don't want to do that, any data that you have recorded in this software, as long as it's historical data, you can import it into this software for free. So maybe you do that at the end of every week or every month, or maybe if you have a really complicated acoustic trace you're trying to analyze, import it into here because it's much easier to analyze in this software. So you can always import it for free into this one. I'll show you how to do that in the in Section 9 when we talk about these softwares. So okay, so we kind of have an introduction to the fluid level gun, how things are working. So let's kind of review real quick. So fluid level shot, you shoot a pressure wave down the tubing casing annulus. Okay, this is frequently called, this is the annulus between the outside of the tubing, inside of the casing, frequently referred to as the backside. Okay, I could call it either the annulus or the backside. Reflections, these are generated by changes in cross-sectional area. They're going to, if there's a change in cross-sectional area like perforations, where there's an increase in area, or a TAC, this is going to send a reflection back. The microphone plots the sound waves on the acoustic trace. So all those reflections come back, are picked up by the microphone. Here's what an acoustic trace looks like. This is from my rod pumping brochure on page 4. So here's the shot, collars, fluid level. Now here's another acoustic trace where I truncated it. I cut off the top of it for space. But you can see we have a down kick for the TAC, an up kick for the perforations. I have this marked as the fluid level. Just realized this was a really bad example. I should have not put this in there. I know the fluid level's here because the seating nipple was right here, right below the perforation. And so it has to be here. But really you can't necessarily distinguish that as being the fluid level because it could be just the rebound from this up kick. Notice on every kick, so for the down kick here, there's a rebound after that. Okay, so anyways, the polarity of kicks. So if you don't understand down kick, up kick, well, let's talk about that. So there is a difference in the way that it's plotted based on what comes back to the microphone. So if that pressure wave, as it's going downhole, if it sees an increase or an opening in the area, in the cross-sectional area, that is going to come back as an upkick, or it's going to be plotted as an upkick. And this is an upkick. So going from left to right, it first kicks up. Okay, and then it has the rebound down. That's what I was talking about right here. But what matters is what does it do first, going left to right? It first goes up. So an upkick is a reflection of the fact that it's something called a rarefaction wave. So remember, we were looking at compressive waves. When we take a shot, we create higher density. These are all compressive waves where they're slinky, essentially. And remember, we're doing that with the gas medium, a little focalized place of higher density. Well, as that wave's going down, if it then sees an increase in area, so as it's coming down, it sees that's going to create a localized area of lower density that's going to send a reflection back. That's called a rarefaction wave. And that's why it's going to plot as an upkick. It sees a little lower density wave coming back to that microphone that's picked up. Okay, so back to polarity of kicks. So if that pressure wave sees a decrease or restriction in cross-sectional area, that's going to be a down kick. Okay, so this is what a down kick looks like. Going left to right, it goes down, and then we have the rebound. Keep in mind that rebound right there. I used to make a lot of mistakes. I'll describe that later on in the section as to how I was sometimes misinterpreting that in situations like this right here. Okay, so another important thing is the amplitude. So there's a polarity of the kick and then the amplitude. This is proportional to the change in area, okay, or the energy reflected. So as that wave is coming down, based on how much it deviates from zero or the baseline right here, it'd probably be better to look at this one. So if we look at this one, here's 0, and you can see the TAC's got a little amplitude, but this perforation, the amplitude of that is much bigger, which means it's reflecting more energy back, which means there's a larger change in area right there. It is reflecting more of the energy back, and that's important in helping to identify things as to what you're looking at, and we'll look at some examples of that. So here's our fluid level gun hooked up with our tubing. We got some tubing collars. Pow! We take the shot from our volume chamber, inject gas there. We create that compressive wave. That wave goes down. Any change in cross-sectional area, including tubing collars, are going to send a reflection back. Eventually, what is left over is going to bounce off the top of the fluid level, come back to our microphone. So here is our shot. Here are tubing collars, all these little down kicks. A collar is going to be a reduction in area because it's larger than the body of the tubing. So these will all be down kicks. And then here's our fluid level. Okay, and our fluid level is it's a low frequency event, meaning you can see how much space is occurring right here with respect to our timeline. Okay, as opposed to these other kicks right here, these down kicks, you can see the black lines basically on top of each other. This is considered high frequency. That'll be important later when we talk about different types of filters. So there's something very important called the round trip travel time. Okay, and what do you think that stands for, or what does that mean? Round trip travel time. Well, it's the travel time for it to go round trip. What's round trip? Well, the fluid level goes down, or excuse me, the pressure wave goes down, reflects off the fluid level, and it comes back. So the round trip travel time is how long it takes to get to the fluid level and back. Okay, and that is going to be displayed up here on this upper axis. So this is seconds, and really it's not just for the fluid level. You can look at the round trip travel time for any kick or anything, any collar. If I wanted to know what the round trip travel time of this collar was, I'd go up here and that's 2 seconds. So that's how long it took to go down and back up to that particular collar. So remember, there's 2 axes here. This is seconds on the top one, and this is the calculated depth in feet. Now to calculate the distance to anything, especially the fluid level, that's usually what we want to know. The distance equals the acoustic velocity times the round trip travel time divided by 2. Okay, so it's just the velocity times seconds. Now, why do we have the round trip travel time divided by 2? So in order to calculate the distance to the fluid level, that pressure pulse has to go down, hit the fluid level, and come back. So it's basically traveling twice as much as what the distance is to the fluid level. So let's just say if the fluid level is 100 feet down, it has to go 100 feet down and then 100 feet back. Okay, but we just want to know how far it is from surface. And so we divide by 2 to account for the fact that it has to travel twice the distance. And this is how we calculate the distance to the fluid level. So if you look, the primary way of calculating the acoustic velocity, it's going to be done automatically in the software. The software will try to. And right here in the collar count, again, here's our acoustic trace. These are different collars right here with our 11-point divider, where we try to get on point right here. And as a result of this, it's going to calculate the acoustic velocity based on how many collars it's seeing per second and understanding what the average length of tubing is. For this particular well, the acoustic velocity is going to be 1,219 feet per second. But you always want to verify that the software has a reasonable acoustic velocity. This is kind of your quality control check to make sure. You don't want it to be 500 or 1,800. That's really beyond the bounds of anything reasonable. It should be between 800 on the very low end to probably 1,350 on the upper end. Okay, so our round trip travel time, here's our fluid level shot. Okay, and our round trip travel time to this kick is 10 seconds. So that's where the pressure wave goes down, comes back to the microphone. So if this is surface right here, you can imagine that shot's going down. Here's the fluid level, reflects back to the microphone. That's our round trip travel time. This is kind of a review right here, but I'm going to make a point. So the distance equals the velocity times the time, as we just went over. And this is the equation we just discussed. So we're just using the acoustic velocity, which is how fast does the pressure wave travel in the gas medium. And then we're recording what the time is. Basically, there's an internal clock in the software that's just counting time. We divide it by 2 because it has to go down and back. But the big question is what is the acoustic velocity? So as long as you have a good acoustic trace and you can identify the fluid level kick, which is not always easy, and we'll look at examples of that, but as long as you can pick out the fluid level kick, you'll know what round trip travel time it showed back up to at the microphone. But then the big question is, what is the acoustic velocity? And usually this is pretty straightforward, and sometimes it's extremely complicated. We will look at some examples of that. So there's various different things that can cause the acoustic velocity to move at a different speed, and primarily it's the composition of the gas. So do you have methane, ethane, propane, CO2, H2S? What is the composition of the gas? That's going to affect how fast that pressure medium transmits. Also, what is the temperature and pressure on average of that gas? That's going to affect the acoustic velocity, but we will look at that later in this section. So here's an acoustic trace, and the fluid level, our LL line, liquid level, is right here. You can see this says shot. Here is when the shot was taken. Here is the fluid level, and these all right here are repeats. Okay, so what's happening is our fluid level gun's at surface. This is the wellhead. Here's the fluid level, and it's just bouncing up and down, up and down. Okay, so the energy hits off fluid level, comes back to the wellhead, down to the fluid level, up to the wellhead, and it's going up and down, up and down. So here is where the fluid level kick shows up. And all of these are repeats off of that, okay? Now notice that the energy is decreasing. We have decreasing amplitude each time because the energy is being dissipated due to friction. Friction is always removing energy as it transmits up and down. So you can see the amplitude of this kick is here, and then it starts decreasing. Here's a kick, here's another repeat. Now the next repeat, these are all equal distance, okay? The next repeat should be at an equal distance, which I think would be probably right about there. It's hard to actually certify that that is the case. The next one, I don't know. So at this point, the noise to signal ratio is too great. We cannot distinguish it. Okay, but we don't have a problem of identifying the fluid level. It's really high right here, but notice that it will decrease, the amplitude will decrease as the energy depletes. So that is the end of this video. In the next video, we are going to pick up on polarity of kicks, looking at some of these things right here for up kick and down kick.